This conference will now be recorded.
Hello everyone, hope you are doing great. Today I continue the yesterday class about the energy balance using a steam table on a 1 and 2 component process. So when you have 1 or 2 components, so far we usually practice on 1 component. Always you have just 1 component inside and the other component, the same component outside. So today I practice with you some examples about 1 and 2 components process to get to know how to do energy balance for these types of process. So this is the example we have about a 1 component process when 2 streams of water enters a boiler. Let us to read it together first. So 2 streams of water are mixed to form the feed to a boiler. Process data are as follows. Stream 1 enters at 120 kg per minute at 30 Celsius, and stream 2 enters at 175 kilogram per minute, and the temperature is 65 Celsius. Boiler pressure is 17 bar absolute. The exiting steam emerges from the boiler through a 6 centimeter ID pipe. Calculate the required heat input to the boiler in kilojoule per minute if the emerging steam is saturated at the boiler pressure. Neglect the kinetic energy of the liquid inlet stream. So what we have so far, we know that all of them are the same component, that is water, in 2 different phases. Inlet is liquid water. Inlet is liquid water at 2 different temperature and 2 different mass flow rates. The boiler pressure is given to you, it is 17 bar, and moreover, the exiting stream is saturated steam at boiler pressure, which is 17 bar. So as we read, and the other assumption of the question is that the kinetic energy of the inlet streams are considered 0. So in that case, we can consider kinetic energy or velocity in the inlet streams, which is these 2 streams, is considered 0. So the first thing we have to start, as usual, is to start with the flow diagram of the process. So here, that is a boiler with 2 inlet stream with 2 different flow rates and 2 different temperature, which enters the boiler and leave the boiler in saturated steam. The inlet is liquid water, outside is saturated steam. You are given the ID of the outlet, so you can probably calculate the velocity of the outlet. So velocity you have to calculate. I changed the ID to the radius and change it to meter for your own easiness. So what we are asked from this question, we are asked for energy required to be actually supplied to the boiler to do this actually process for us. The other assumption of the question is that kinetic energy of the liquid inlet stream is considered 0. So V here is considered 0, but we have kinetic energy here. So we are clear about whole process, that all of them are engaged with just one component, which is water only. So as usual, we start with the energy balance because we need Q that we can calculate through the energy balance equation. So we start with writing the energy balance equation, which is delta EK, delta EP, delta H enthalpy, and Q minus WS. From the boiler structure and the question, we know that there is no work of the shaft for the boiler, and the other one, there is no specific elevation or actually changes of the height between the inlet and outlet, so you can assume delta EP is considered 0. By considering delta, by crossing delta EP and WS as the term that are considered to be neglected, you have delta EK and you have delta H, that which will equal to heat. So to calculate the heat that is supplied to the boiler, you have to calculate the changes of the kinetic energy plus the changes of the enthalpy of the inlet and outlet stream. So I just wrote what is the delta EK. We start with each component. First, we start with delta EK, then delta H, and then we can calculate Q easily. So what is delta EK? Delta EK is considered EK outlet minus EK inlet. EK inlet, based on the problem assumption, is negligible or considered to be 0. So what is left is kinetic energy in the outlet. So that is a formula we know about the kinetic energy. I put 3 because we have 3 streams, 2 stream inlet and 1 stream of the outlet. Here, to be able to calculate this term, we don't have mass flow rate at the outlet, we don't have velocity of the outlet. So these two terms should be calculated. So we start each of by m dot first. Calculating the mass flow rate here is easy because you already have mass in. To be able to calculate the mass out, you just have to, because these two are adding to the boiler and exit at the outside. So mass out is equal to sum of these two masses. Agree? So that is the way we can calculate easily the mass in the outlet of the boiler, that which is equal to mass in. The first one is 120 and the other one is 175. So it will be 295 kilogram per minute. To calculate velocity, we want to use this formula. So we already discussed about this formula to calculate mass flow rate. Mass flow rate is equal to rho V, volumetric flow rate, or rho AV. We already know about A because the diameter of the outlet is clear. We want to calculate this one. We know about M3, and we have to know about density. So I just rearrange this formula based on V3 that we want to calculate. So M3 we already calculated from here. I just substituted and converted minute to second, as you can see here, right? Now we need rho, or density of the outlet, and A. A is easy to calculate because the is already given to you. What is the ID of the outlet of the boiler? So we need rho. As you remember, to be able to calculate the rho, you can use the specification that you have in a steam table, because density is reverse form of a specific volume that we can find in a steam table. So as long as you can find a specific volume, you can reverse it and calculate the density. How we can calculate? How we can read about what is the specific volume of the outlet? Because it is saturated steam, as you remember. For saturated steam, you can refer to table B5 and B6 based on the input data and select the property you want. We need actually a specific volume for saturated steam. For the pressure is given to us 17 bar. As long as we have pressure, we have to refer to table B6 because the data is arranged based on the data there is arranged based on the pressure in table B6. So I just read it from table B6 at 17 bar. A specific volume for steam, right? Because it is saturated steam based on the assumption of the problem. So I read it. This is a value. So reverse value of a specific volume is considered density. You can see the unit of a specific volume and the unit of density. So this is a value of the density that we substitute here to be able to calculate the velocity of the exit. As long as we have the velocity of the exit and actually even the mass flow rate of the exit, it's easy for us to calculate this delta E term. So I just substitute all the data that we have. I just substituted it inside the equation and calculate it. Because we have, this one is per minute, that one will stay per minute. I didn't change minute because based on the problem, we need to know Q based on kilojoule per minute. So I kept the minute unchanged. But even if you change at the final stage, you can change again. So after finalizing calculation delta EK, we need to calculate delta H. Delta H is very clear because you already have, you can refer to the table and read the H enthalpy of the inlet and outlet, and easily you can calculate delta H. How we did that? Here. So that is the H out minus H in, because we have two streams in the inlet, so we have to consider the sum of both as the H in. Okay, clear, right? So H out is the H of the saturated steam that exit the boiler, and H in is the sum of the two inlet stream that enter the boiler. If you have more than one stream from the same component, you have to add them together if they are entering the facility. Even if you have more than one stream from the outlet, you have to consider all the outlet as the H out. But you have to add them together, and then this is H out, this is H in. So we need to read or find these values from the table. We know H1 and H2, the temperature they are giving to us about H1 and H2. We know they are liquid, right? And the temperature is given to us. Easiest way, we can go to table B5 because that table is arranged based on the temperature. So because you have to read you have to find out for 30 Celsius of temperature the specific enthalpy for water because it is liquid. So if you refer to the table, you will find out these properties. The same way for stream 2, at 65 degree, you have to read it from the table. Please pause the video here, go to table B5, search a specific enthalpy for liquid at temperature 30 and 65. And I want to be sure that you are finding this value inside the table. So now, as long as we have a specific volume, finding the specific enthalpy, finding the enthalpy rate is not a big trouble because you have to just sorry, this one is, I'm sorry, I made a mistake here. This one is a specific volume, a specific enthalpy, right? It should be wrote by like this one. I'm sorry about that one. It is a specific term. As long as you have a specific enthalpy, if you multiply it by mass flow rate, you can get enthalpy rate. But the only thing you have to consider, for each stream, you have to consider that mass rate. Okay, for first stream, mass rate is 120, and the other one is 175. So these two are the values. And the multiplication of these two values are the kilojoule per minute of enthalpy. So now we have to go to H3. So H3 is saturated steam at 17 bar, right? So it's not difficult there. You can go to B6 because it is saturated steam. To table B6, pressure is 17 bar. Pause the video and check if the specific enthalpy you read in the table is equal to the same value. again here I were supposed to put this one. Sorry, I forgot. So this one should be by these symbols, right? So through this, by multiplying by the amount of the mass flow at the exit, that is 295, you can calculate the enthalpy rate in the outlet. So the rest is clear because you just have to calculate delta H first by putting inside above formula, and then Q is clear, delta H plus delta EK. We already know this one. We already know this one. Both of them are based on kilojoule per minute. You already calculate this term here. The other term you calculate above. So, and both of them has the same unit, kilojoule per minute. I just substitute these two elements and calculate final Q. This is the amount of the energy that be released by the boiler because of this temperature difference. Sorry, that is the energy should be provided to the boiler to that is the energy should be provided to the boiler to run this process. That is what it is positive, right? So I hope it is clear here. Now we continue with the next example. I give you next example for your own, for yourself to solve, but I will try to solve it for you now. So that is the way we calculate the required heat input to the boiler in kilojoule per minute, right? So what is the next example? This example is talking about two components, because as I am reading this question, you will see there are two different components involved in this facility. Saturated steam at gauge pressure of 2 bar is to be used to heat a stream of ethane. A stream of ethane. The ethane enters a heat exchanger at 16 degree and 1.5 bar gauge at rate of 795 meter cube per min and is heated at constant pressure to 93 degree. The steam condenses and leaves the exchanger as liquid at 27 Celsius. The specific enthalpy of ethane at given pressure is given to you, because for ethane you don't have the table you can refer, but for steam you can refer. So you don't have any problem. They already give to you the specific enthalpy of the ethane at two different temperatures that they already give it to you. That is the temperature that it enter, and that is the temperature that this one exit. How much energy must be transferred to ethane to heat it from 16 to 93? So we are talking first about ethane, right? We want to see how much energy should be transferred to ethane to heat it from this temperature to the exiting temperature. So first we have to start with the flow diagram of the process. We have a heat exchanger. For sure, you have one cold stream, you have one hot stream. The cold stream that it start, actually ethane start in 16 and have to leave, it should be heated up 16 and actually leave at 33. To do this process, steam, saturated steam is doing this process, that saturated steam enter the heat exchanger at 2 bar in saturated steam condition, but at the exit it leaves the heat exchanger in liquid form and 27 degrees. So it is a stream that get cooled off because of the heat exchange. So hopefully you already started to draw the flow diagram of the process first. Then I will start with the solution. So that is very important for you that you show this flow diagram. So we have ethane, as the problem told you. We have ethane that enters the, you can actually show it like a heat exchanger. I just show just a block. That ethane enter the heat exchanger at temperature 16 Celsius and leaves at 93 Celsius. Okay. The pressure of the inlet, pressure of gauge pressure is 1.5, and it leaves in the same pressure, 1.5 bar gauge, and it leaves in the same pressure. They already give it to you, volumetric flow rate of ethane in the inlet, 795 meter cube per min. They give you a specific enthalpy of the ethane at this temperature, and they have to give a molecular weight of ethane to you as well, that I put it here. So at the outlet, the temperature is given to you, the pressure is similar to the inlet, and the specific enthalpy is given by the problem to you. So I just arrange them in the position of them. And meanwhile, saturated steam enters the heat exchanger at this pressure gauge. You have to consider absolute pressure for your calculation. So I actually did some changes, the conversion from the gauge pressure to absolute pressure, right? So I read a specific enthalpy, because you need a specific enthalpy for your calculation of energy balance. I read a specific enthalpy from B6 based on these, actually 3, even you consider 3 is okay, assume it is 3, at 3 bar for saturated steam. That is what I read from the table, that you can pause the video and check inside the saturated steam table in B6, as I explained to you in the previous session. And this water leave the heat exchanger in, actually this saturated steam leave the heat exchanger at liquid water form or water form at this temperature, right? At this temperature, 27 degrees. This specific enthalpy, I read it from the table. However, because exact value was not available in the table, I interpolate. I had the value of the specific enthalpy at 26. I had the value at 28. So I interpolate at 27. How was interpolation? I told you. Just write the slope formula for 2 points. This one minus this one divided by this one minus this one is equal to this one minus this one divided by this one minus this one. That I just wrote the slope of this and these 2 lines, and now this and this line. So and then I calculate what is the specific enthalpy at this specific temperature from table B5. That one I read from B5, because when you have temperature, it's easier to go to table B5. So these are the whole information I extract from the problem and from the steam table. So I want you pause it for a while. Be sure that you can read and calculate a specific enthalpy of the water at this temperature and a specific enthalpy of the saturated steam at this absolute pressure. So this is first you have to find out. What I did more to just make the calculation easy, as you always wanted, I changed this value to, just in case if I need Kelvin value, I just calculated to the Kelvin value. You can calculate if you want. You have to change all the, you have to convert all the gauge pressure to absolute pressure. you know how to calculate absolute pressure. To calculate absolute pressure, you can add the atmospheric pressure, that is this value, to the gauge pressure. So you will have absolute pressure by this conversion, right? Here they gave me volumetric flow rate in meter cube per minute. I converted to the second, meter cube per second. Here for the molecular weight, it was gram per mole. I converted to kilogram per mole to make calculation easier. These are just some calculation because you always wanted me to do conversion before starting to solve the question, right? So I hope that you can draw this flow diagram before you start to solve the equation, solve the problem, because it makes your process so easy. So we start from, as we always mention, we start from energy balance equation. Sorry, I sometimes forget to put these dots. You put it, right? That is not a big deal, I hope, because all of them are dots, right? All these terms are dots. Okay. So I just rearranged the formula based on the assumption we had, right? The first assumption you have, there is no elevation, there is no changes of the position of the inlet and outlet. You can consider, even if it is a small amount, it is negligible as long as they didn't give you any specific amount for changes of the height. Delta EK is 0. They didn't give you any information. You can consider they are somehow, it is near 0 or negligible. There is no shaft work in this problem. So what if you remove all these terms? What we leave here is just delta H and Q. So first of all, we write just energy balance just for the first component, that is ethane, right? So we know changes of the delta H means H2 minus H, and Q is Q. So this one, if we have the specific, and because they give us a specific enthalpy, we have to multiply it by mass flow rate to calculate enthalpy rate. Great. So I just because it is m dot for the ethane, the same m is entering and actually exiting the heat exchanger. I just factorize it, put it here, and then that is the two elements you have. You have H2, the problem is given to you. You have H1, it is given to you, but you don't have mass flow rate for the ethane, but they give you volumetric flow rate. They gave you molecular weight. So I'm sure you remember from each formula you can calculate the mass flow rate. Mass flow rate, this is the old formula that we learned together. That is mass rate is equal to density multiplied by volumetric flow rate. And if your rho is PMW RT multiplied by V. This is another way to calculate rho. But if you have a specific volume, you can just easily calculate rho. But in this case, you don't have a specific volume. So you have to back to this ideal gas formula. So PMW RT, you already have P, you have MW, you have R, you have T, and you have volumetric flow rate. So you just substitute in this formula. Everything is clear. That one is bar, it should be absolute pressure. That is the molecular weight. That is R, because liter was here, I just converted to meter cube. Last one is the temperature. Here is volumetric flow rate. To do this calculation, you know how much is the mass flow rate. That one is just for ethane, right? Because there are two different components. For each component, mass is constant. Mass in is equal to mass out. You know that. If it is water, it is ethane. They cannot change the components by any reaction inside. Sorry, not by even if there is reaction, for sure you have new types of the material in the outlet. But because it is just physical changes of the heat in the boiler, ethane enters and ethane exits. So the mass is constant for the ethane. So as long as we have mass of ethane, we have a specific volume, a specific enthalpy of outlet and inlet, we can just substitute and calculate the Q for heat. So that is the first part, that they ask you about the heat, which is required to heat the ethane from distance from 16-degree temperature to 93 degree. So now we go back to the second part of the question. So we already calculate how much energy must be transferred to ethane to heat it from 16 to 93. In the second part, they mentioned, assume that all the energy transferred from the steam, assume that all the energy transferred from the steam goes to heat the ethane. So what does it mean? Means whatsoever ethane received here is from the steam temperature changes, or actually energy transfer from the steam. So now tell us or calculate at what rate in meter cube per second must the steam be supplied to the heat exchanger. So that is the assumption from that it say all the energy by the steam was transferred to the ethane, right? So how you can interpret this inside your calculation? Can you think about that? So I apologize if anywhere inside your solution I forgot to put this dot. Please you put it, right? I'm sorry about that. So you just have to put dot dot because it's your. So what I did, I write the mass energy balance for water now. The same energy balance, delta EK, changes of kinetic energy, changes of potential energy, changes of enthalpy equal to Q minus W. So we don't have all these terms are considered against zero. So delta H the same way is equal to Q. We don't have this one. We don't have mass rate of the steam, because this one we wrote it for a steam. So every component should be for a steam. Mass rate of the steam we don't have. H2 and H1, I read it from the table. So we have these two components. Q we don't have. But based on the assumption of the problem, whatsoever energy was received by the ethane was lost from the steam. So the same value of the Q that we calculate for the ethane was lost by the steam. That is why I put negative 5,487. We calculate this value for ethane, right? The problem is telling us all the energy from the steam received by ethane. So means that if this amount of the energy, ethane received to do the temperature changes, the same amount of the energy was lost by the steam in the process. Because it is lost by the steam, we consider it is negative, right? Down. That is why I put negative value. Negative value. Yeah. Here is negative value because steam lost this heat and ethane received it. These values we calculated from the, we actually read it from the table as I show you in the beginning, right? I read the values from the table. I show you here how I read these values from the table. I explained to you already. So we're back to our calculation. I just substitute whatever we had. We didn't have mass rate. But based on this all known component, I can calculate the mass rate. That is a mass rate based on this calculation. If you have mass rate, now you can calculate. They ask us for volumetric flow rate, right? If you already have the volumetric flow, sorry, if you have the mass rate, you already, if we can know what is the density of the steam, we can calculate volumetric flow rate. We need volumetric flow rate for a steam. So we already calculated mass rate here, so we just know. What about the density? So we can actually reach to the density of the saturated steam because we can calculate the density as the reverse form of the specific volume. Because it is for water, you can read a specific volume for saturated steam from the table. We know the pressure is 3 bar. We can refer to B6 and read the specific volume. Reverse form of a specific volume is the density. As you know the density, then you can calculate how much steam you need for that assumption that the question asked for. That is 1.27 meter cube per second. Hope you understand these two questions as well. Please, if you have any question, let me know. I can explain for you more. Have a nice day. Bye.